In this video, we are going to focus on linear systems. So we are going to write them down, some homogeneous, some non-homogeneous, and then we need to rewrite them in what is called augmented matrix form. Once we know how to go from the system and write it in augmented matrix form, and also back from augmented matrix form, we rewrite the system. That will be one of the techniques that we need to master very quickly. We will see something called elementary row operations, because my matrix will have columns that stand up and rows that are sleeping. So there are operations that we can do on rows. They're called elementary, and they are very important, and we are going to use them all the time for the rest of the class. I mean, for the rest of the semester. So these operations are very important. That's the focus of this lecture, is how to write a system, rewrite it in augmented matrix form. So let's start with that. So I'll start first with the system. So given a system, so now we just write some equations. So let's say plus x4 for fun equal to 2, and then let's say x2 plus 2x3 plus 5x4 equal to 1, and why not x minus 7x1 plus x4 equal to 0. So this is our system that has three equations, so all three of them, and we have x1, x2, x3, and x4 as variables. So we have four variables, and three equations. Not big deal. Okay, we are not going to solve it yet. The idea is just to see how to write it in matrix form and then how to write it in augmented matrix form. So write the system in matrix form, and then you will see how to write it in augmented matrix form. It's a big deal. So first thing, I need to write my matrix. So what is a matrix? It's a container, and the brackets, normally we use square. So this will imply a couple of things that we haven't seen yet. We'll see later on. Multiplication of matrices. But this is just to make sure that you get exposed to the notation. So let me just... Okay, so my variables are here, x1, x2, x3, and x4. So this is vector of variables. Or unknowns. Okay, on the right hand side I have 2, 1, and 0. So this is called right hand side, or in more advanced classes, source term. But okay, let's be elementary. Okay, so right hand side. And now, how do I fill the matrix? Well, implicitly I'll show you even how to multiply a matrix in a vector. So you see in front of x1 I have 2. In front of x2 I have minus 3. In front of x3, it's 0, because x3 is not even there, it's 0 times x3. And in front of x4 is 1. So here I will write those coefficients. So 2 for x1, a little bit of space, minus 3 for x2, a little bit of space, 0 for x3, and 1 for x4. So it's like 2 times x1 plus minus 3 times x2 plus 0 times x3 plus 1 times x4 equal 2. That's how you read it. So this is a product of the first row, this is called a row, with this vector of unknowns. So let's go for the second one. In front of x1 is 0 because it's 0 times x1. And then in front of x2 is 1. In front of x3 is 2. Whoops. And in front of x4 is 5. So I have 0 times x1 plus 1 times x2 plus 2 times x3 plus 5 times x4 equal to 1. Okay, the last one was minus 7 in front of x1. Then in front of x2 is 0. In front of x3 is 0. And in front of x4 is 1. So I have 7 times minus 7 x1 plus 0 x2 plus 0 x3 plus 1 times x4 equal 0. So this is a non-homogeneous system because on the right hand side I have at least one of the entries of the vector is different from 0. Actually there are two of them here. So this is a vector, this is a vector, and these are the entries. So just write non-homogeneous system. Okay, and this matrix, because this is a matrix, it has 3 rows and it has 4 columns. Each column for one of the variables, of unknowns, and each row for one of the equations. So this is called coefficient matrix. Because this matrix contains coefficients for the system. The size of the matrix is 3 rows and 4 columns. So let's write somewhere. Size of the matrix is 3 rows by 4 columns. So later on we'll drop rows and columns. We know that first number is for rows and second for the columns. So we will say that this is 3 by 4 matrix. Later on we will see that this can be also called a matrix even though it's a vector. We will say it's 4 by 1. And this guy is 3 by 1. 1 column, 3 rows. 3 by 1. Okay. So that's what we do. How we find from a system a matrix form. We have a matrix containing coefficients called coefficient matrix, and then variables in one vector in correct order, and then we have the right hand side member in correct order also. So let's say I have this and I want to write this augmented matrix form. Well, it's not a big deal because we know who are the unknowns, x1, x2, x3, x4, they don't change. So I don't need to write this all the time. I can simplify a little bit my notation. What I need for sure is this coefficient matrix, for sure, and I need these guys here, the right hand side member. Unknowns, I know who the unknowns are, like implicitly. So let's write now augmented matrix form, and you will see it's just a joke. It's not a big deal. Write the augmented matrix form of the system. So I'll keep part of it because I need it. So I will have my coefficient matrix, I'll copy paste, not a big deal. And then 0, 2, 0, 1, 5, 1. So now is the trick. Now I don't need these because I know what are the variables. So the solution of the system is about getting the numbers or expressions for these unknowns. It has nothing to do with, well, nothing to do with this guy. this is not a solution of the system. Solution of the system contains 4 components. For x1, for x2, for x3, for x4. One for each. Okay? Be careful. So now, what I do, and in your book sometimes they are lazy, they don't put the bar. So this separates coefficient matrix from the right hand side member. So the first one is 2, then I have 1 and 0, and I close it. Okay, so this is the augmented matrix form of the system. Okay, this bar separates coefficient matrix from the right hand side member. And very quickly we will see why this is important and why this is useful actually. It's not just notation for nothing, it's very useful when we want to solve problems. Okay? So let's have another one. So this one was non-homogeneous. So let's find one that is homogeneous. So let's say I have something like x1 minus x3 equals 0, and then x1 plus 2x2 minus x3, okay, plus x3, whatever, equals 0. Okay, this system has 2 equations and 3 unknowns, and this is homogeneous system. Why homogeneous? Well, both equations are equal to 0. That's the definition of homogeneous system. When the right hand side member has only zeros inside. That's homogeneous. Very quickly this will be useful. That's why we introduce these names. So let's go for matrix notation and then I'll go for augmented matrix. Later on you will write augmented matrix straight away, it's going to be faster. So I have my coefficient matrix, and then I have vector for unknowns, and then I have vector for the right hand side member. So these guys are 0 and 0. Unknowns are x1, x2, and x3. Good. Now I need to fill in this coefficient matrix. So in front of x1 is 3. In front of x2, well, it's 0 because it's 0 times x2, and in front of x3 is minus 1. Okay. In front of, so that's the first row. So this is the first row, this is the first column, second column, third column. Okay, so the second row is for the second equation. In front of x1 is 1, in front of x2 is 2, and in front of x3 is 1. So row 1, row 2, column 1, column 2, column 3. So this is matrix that is 2 by 3. Size of the coefficient matrix is 2 by 3. Okay, read 2 by 3. Okay? So times it's by. Good. And this is homogeneous. So let's now write augmented matrix form. Well, that's not complicated. All I need to do is copy my coefficient matrix. So 3, 1, 0, 2, minus 1, 1. And then put the bar. And then put 0, 0 on the other side. Ta-da! Finished. Very nice. So what if I give you augmented matrix form and you need to give me the linear system? Well, that's not complicated again. So later on, when we need to actually solve these systems, we will go quickly to the augmented matrix form because that's the one we really need to work with. So given the augmented matrix form, so let's say 2, 7, 1, 0, minus 1, minus 2, let's say 0 again, and then 4, and then 0, and then minus 7, and minus 5, minus 1, 0, minus 3, 2. We normally put nice numbers because we don't like to work with ugly numbers, but in real life, these numbers could be any real numbers, that they don't need to be cute. So we have this augmented form, right? The corresponding system. So write the corresponding linear system. So that's not a big problem. What this means? It means 2 times x1 as a first in the first equation, plus 0 times x2, I'm not going to write it, plus 0 times x3, I'm not going to write it, minus 7 times x4 equal to 0. Okay, that's the first equation. First row is for the first equation. On the right hand side is the guy after the equal sign. Okay, second equation. Second row gives coefficients. 7x1 minus x2, 4 plus 4x3, and then minus 5x4 equal to minus 3. Ta-da! So I have my coefficients all right in the right order. Now the last equation, first coefficient is 1, so 1 times x1, x1, minus 2 times x2, plus 0 times x3, I'm not going to write that, minus x4 equal to 2. Ta-da! So this is my system with 3 equations and 4 unknowns. So I have each column corresponds to one unknown, and each row is for one of the equations. So that's the idea, how we go from one to another. Okay? Good, so now we know how to go from system to augmented matrix form and from augmented matrix form back to the system. What I want now is to introduce 3 elementary row operations. So they work on rows, so on the lines, on the sleeping part of the matrix. We will see how they are useful and important. So we have 3 elementary row operations. What does that mean? I have my matrix, ideally in augmented matrix form, when I solve the systems. And there are 3 operations that I can do on the rows that are legal and useful to us. The idea is that those operations will not change the solution set. So if your original system has no solution, when you apply these elementary operations, at the end, well, the system that you get will still not have a solution. So that's fine. If your system from the beginning has one unique solution, by applying these elementary operations, at the end of the process, your system will have exactly one solution and it will be exactly the same as the solution for the original system. Well, that's interesting because we can simplify the systems. That's what we are going to see in Gauss-Jordan solution method. Okay, so those are important things. That's why elementary operations are interesting. So first one, so let me write a matrix just for fun. So let's say I have 3 rows, it's enough. So 2 minus 1, 0, 3, 1, 1, and let's say 4, 1, 2, And on the other side, let's say -1, 0, 2, whatever. So this is my augmented matrix form. So I have three elementary operations. First one is swap between two rows. They have a very sophisticated expression, interchange of two rows. Of two rows. Which one? Well, you choose whichever one, doesn't matter. The question is what is useful. So you can swap two rows, and that will not change the solution set. That's great. We remember that equations put constraints on variables. So if I swap the order of equations, order of constraints, well, that doesn't change anything because I still have the same three equations, the same three constraints. They're just expressed at different moment. Doesn't change anything for the solutions. I can multiply one of the rows, whichever I choose, by any number different from 0, and that will not change a solution set. That's beautiful. So multiply a row by a non-zero constant. So I can choose any number I like except 0, and I can multiply any row I like by that number. So I multiply all the coefficients on both sides of the bar. So if I choose row 3 to multiply by 7, well, I will multiply this by 7, this by 7, this by 7, this guy by 7. And that will not change the solution set. That's beautiful. And the last operation is the one that we use the most. What we can do is replace one of the rows by that row plus or minus some number times some other row. So let's call it replacement. We will see this, and this is the one we are going to use non-stop. And the beauty of it is it doesn't change the solution set. So elementary row operations do not change the solution set of a linear system. So that's the beauty of it. We don't need to prove it. We take it as a result. It's gorgeous. So let me illustrate each single one of them on this system. And later on we are going to use it non-stop. Okay, so swap, multiplication, and replacement. So let's have one. And pay attention to the notation. It will be interesting. So let's say I illustrate the swap. So let's say I swap row 1 and row 3 for fun. Row 1 and row 3. Okay, this is the sign for the swap. I could choose row 1 and row 2, doesn't matter. So what does this mean? Row 1 and row 3, they change place, they swap. So the resulting thing is, so row 1 becomes row 3 and row 3 becomes row 1. So I'll have 1, 2, 0. So the last row becomes first row. The first row becomes last row. And then the second row, we didn't touch it, so it stays as it is. So that's what happened. We swapped row 1 with row 3. Just swapped. Nothing special. second one, multiplication. So I multiply by a constant. Let's say I replace row 2 by, row 2 times some number, let's say 6. So normally you will put number before. So 6, row 2. So what I'm doing is I'm replacing row 2 by 6 times row 2. So how does it look like? Well, since first and last row don't change, I'll copy them first to simplify my life. So I don't make copy-paste errors, so I can double check. So first and last row don't change. Now the second row will change, and in its place will come 6 times the numbers here. So it's 6 times minus 1 is minus 6. It's 6 times 1 is 6, and it's 6 times 1 is 6, and then it's 6 times 0, which is 0. Okay, so that's what happened. The only change is that the row 2 was replaced by row 2 times 6. And the last one, that we use a lot, replacement. Let's say I replace row 1 by row 1 plus 3 times row 2 for fun, just like that. So row 2 and row 3 don't change, so I'll copy them. Okay, so now I need to know how to add and multiply single digit numbers. So you see row 1 is the victim, and row 1 comes the first here. Very important. There is nothing in front. This guy, there's 1 in front, okay? Nothing else. Plus or minus, whatever I decided, 3 times row 2. Okay, so how does that work? Well, I need to take entry 2 from row 1 plus 3 times entry from row 2. So 2 plus 3 times minus 1. So that's 2 minus 3, right? So that's minus 1. Then the second entry, it says you take it and you add 3 times the entry from the row 2. So it's 3 plus 3 times 1. So 3 plus 3. 6. This guy is 4 plus 3 times 1. 4 plus 3, 7. Last part is minus 1 plus 3 times 0. Well, that's 0, so minus 1 plus 0 is minus 1. Ta-da! There it is. Okay. Another example with the replacement. So let's say I take row 2 and replace it by row 2 minus 2 times row 3 for fun. So row 2 is changing. Row 1 is not, so 2, 3, 4, minus 1. And row 3 is not changing, so I keep it. So row 2 is changing. Okay, how is it changing? Well, I take it and then I subtract 2 times the value from row 3. So I have minus 1, minus 2 times 0. Well, minus 2 times 0 is 0, so I keep minus 1. Okay, fine. After that I have 1 minus 2 times 1. So 1 minus 2, minus 1. This guy, 1 minus 2 times 2. So 1 minus 4, which is minus 3. And then 0 minus 2 times 2, so 0 minus 4 is minus 4. Ta-da! There it is. So that's how we do those elementary row operations. And next time we are going to use, actually we are going to use them all the long of the course. And the good and important thing is that these three elementary row operations do not change the solution set of your system. So the solution set of this system and solution set of this system is the same. Okay? Solution set of this system and solution set of this system is the same. And by the way, solution set of this system and this system is also the same. Solution set of this system and original system is the same. And by the way, solution set of this system and this system is the same. Solution set of this system and this system is the same. And solution set of this system and this system is the same. It's the same as this one, it's the same as this one, it's the same as this one. So solution set doesn't change when we apply elementary row operations. That's the beauty of it. And we will take advantage of this all the long of the semester.